7. Ideas about solubility. So solubility is the idea or represents the amount of solute that can be dissolved by a solvent. Now, there are different factors that affect if a solute can dissolve at all versus how much can be dissolved. So here we go. The nature of the substances. So we have this phrase, likes dissolve likes. And what this is referring to is the structure of our molecules. When all of the bonds are looked at holistically, this is an OSNAP idea. Do they create a symmetrical nonpolar structure or an asymmetrical polar structure? So take a look. If we have a polar solvent, so that means it has an asymmetrical lopsided structure, a polar solvent will dissolve or mix with a polar solute. So likes dissolve likes. Polar solvent blends with polar solutes like water and salt, or water and acid, water and base. If you have a polar solvent and it separates, it does not mix or blend with a solute, then we understand that that solute is nonpolar. It has a symmetrical structure. Now, our reference point is water, because we use water in our everyday lives and we have experience of what water will mix with. So water is a polar structure. So you know how to draw water, and when you draw water structure, you always draw it with this bent shape. And if you look at water across like the XY or across the x-axis, the top half does not reflect the bottom half, meaning we have an asymmetrical distribution. So in the realms of OSNAP, water is asymmetrical distributions of bonds around the oxygen, so it's considered polar. So if a solute will dissolve in water, even if we don't know anything about that solute, but we're told it doesn't dissolve in water, then we understand that it is also polar. Likes dissolve likes. It has a similar polarity to water. Similar polarity to water. Which also leads to us, if a solute does not dissolve, it will not blend or mix, it separates itself from water, then we understand that this solute is nonpolar. Or, summary sentence, is that it has an opposite polarity to water. They are not alike. So, if two things blend, they have similar polarities. If they separate, do not blend, then they have opposite polarities. Moving on to temperature. Temperature, we learned earlier in the school year, it's our way to monitor the average kinetic energy of the particles, right? And kinetic has the idea to do with movement. So here we go. As we increase the temperature of the solvent and the solute, the particles in the mixture, we see an increase in every particle's average kinetic energy. All the particles are moving more. The more particles move, we have an increase in the number of collisions. And when we have more collisions, we have an increase in the solubility. So that means that the solute tends to dissolve faster or more easily. So really, in order to dissolve any solute in a solvent, the particles have to collide into come into contact. So dissolving requires the molecules to collide. Now looking at another factor, pressure on the gases. So pressure is a condition that we use to control gas materials. So thinking about Boyle's law here, as you increase the pressure on a gas, it is forced to occupy less space or volume, right? And if this gas is collecting on the surface of a liquid or like a soda syrup, as we increase the pressure on the gas is forced to mix with the water, or the solvent is being pushed down into the solution. So as a general rule, to make a gas more soluble, think about how we store soda before we drink it. Well, we store our sodas at low temperatures, like in the fridge, and we store them under a higher pressure. Well, what creates the pressure, maintains the pressure in a bottle of soda? The cap. Keep it capped, so cap it. So we store our soda in the refrigerator to keep it at lower temperatures, and we put the cap on it, which creates a higher pressure inside the bottle, and more of the carbonation, the carbon dioxide, will stay in the soda syrup. So to keep a gas soluble, this is the opposite idea of the ideal gas. So opposite of the ideal gas. The ideal gas, it wants to be at the beach, right? Keeping our soda carbonated, low temps, high pressure. Force the gas to go where it doesn't want to. The last idea here is the rate of solution. How quickly will the solution form? So as we increase the rate, the solution forms faster, which means it requires less time. So we can manipulate things, whether it's in the kitchen or in the lab, to make a solution form faster. So the first thing that we typically will do is that we will increase the temperature on the solution, get all the particles moving a little bit faster, increase the number of collisions. We can increase the surface size of the solute. So we have, let's say we have a big chunk of the solute. We can crush or grind it. And so what that means is now we have these smaller bits, and now the solvent can get to more of those inside particles that are hidden away in the big chunk. So as we crush or grind our solute, we are exposing more of the particles, more effective collisions. Now the other thing is that we can stir or shake the mixture. Add some more kinetic energy, get those particles moving. So here we go. Now, the other idea here is that as you increase the amount of solute that is dissolved, you actually decrease the rate. It starts to dissolve more slowly. And the reason is that the solvent becomes saturated. And at that point that it becomes saturated, or close to being saturated, it's going to have a harder time dissolving the solute. So as the solvent becomes saturated, it can't dissolve more solute. And that's when you start seeing solute probably collecting on the bottom of a container.